In the name of God, the most gracious, the most merciful. Praise be to God, and may blessings and peace be upon the messenger of God, our Master Muhammad, and upon all his family and companions. And now, by the declining day, indeed, mankind is in loss, except for those who have believed and done righteous deeds, and advised each other to truth, and advised each other to patience. Inspiring the revival of a nation. We will explain how to test overcurrent and earth fault protection practically. Previously, relay testing depended on available equipment. If equipment was available, tests were conducted. Otherwise, they weren't. Electromechanical relays were used then. Now, new American relays are smart and complex, requiring advanced testing equipment due to numerous settings. Real fault simulation is crucial for relays to recognize faults and disconnect. Without this, relays may stay energized. Engineers unaware of numerical relay stages might find relay behavior unpredictable. Testing electromechanical relays once took a day, but numerical relays now require days or weeks to test all logic. This complexity has led to specialized roles for testing engineers. Otherwise, it would stay energized without the relay operating. If you're an engineer unaware of most stages in numerical relays, you might be surprised that this relay sometimes works and sometimes doesn't, leaving you feeling lost. Previously, testing a complex electromechanical relay. In the past, testing an electromechanical relay took a day, but now, testing numerical relays can take days or weeks due to their complex logic. This has led to two categories of engineers during station testing: operator engineers and protection engineers. The operator engineer prepares the test procedure, while the protection engineer applies it. The operator engineer simply presses the button without analyzing results, whereas the protection engineer reads manuals, analyzes drawings, and verifies results. The operator engineer often complicates solutions. I tell you, I applied to test it. I'll it is he who puts it. The operator engineer is the one who says, I just press the push button and I have nothing to do with the results, while the protection engineer is the one who reads the manual and the drawing and analyzes the results, whether they are correct or incorrect. The operator engineer puts a problem for every solution. While the protection engineer provides 1,000 solutions for every problem, the requirement here is to be aware of the 5 stages that everyone goes through during testing. The first stage is called, the second stage is called, the third stage is, the fourth stage is, in addition to the 5th stage, which is, as for the shooting or regarding the testing, it is a test conducted by the manufacturer to prove that this relay or this new relay controller is capable of entering the market strongly and can detect all faults. This proof is for the end user, whether it's electricity companies or any other private companies. Shooting or it is a test conducted by the manufacturer to prove that this relay or this new relay controller is capable of entering the job market strongly and can detect all faults. This proof is for the end user, whether it's electricity companies or any other private companies. They have the final decision to accept or reject this relay. If accepted, it is placed on the relay approval list. A relay goes through complex stages before acceptance, where all fault scenarios are tested, using a special computer restarted for each test. Advanced software and devices simulate realistic faults. For instance, a relay may need to trip at a fault after 9 milliseconds, but if it trips after 50 milliseconds, it is rejected. Only one relay is tested at a time, and approval is for the version that underwent type testing. For example, a Siemens relay, model 7SD version 4.6, if type tested, is approved. Newer versions are prohibited until retested. This is to apply a real and realistic fault simulation. For example, this relay may be required to trip at a specific fault after 9 milliseconds according to its technical data. When this scenario is applied, if the relay trips after 50 milliseconds, it will be completely rejected. At this stage, only one relay is tested. Approval is granted for only one version, which is the version that underwent type testing. For example, if I have a relay from Siemens, model 7SD version 4.6, which is the one that underwent type testing, that is the one that gets approved and placed on the approved list. If there is a newer version, the operation of that relay is prohibited, and it cannot be integrated into the system until it undergoes type testing again. There are some companies that require the manufacturer to conduct type testing for the latest version available, and they strictly prohibit the use of any older versions. There are other companies that require the condition that this relay has been used in the international market for 5 years without any issues before they can use it in their system. Factory testing occurs before a release leaves the factory. Tests focus on verifying model numbers, checking connections, and components. An advanced release's factory test may last under an hour, while on-site testing can take 4 to 5 days. Typically, end users send engineers to witness these tests and ensure safety before the release leaves the factory. Ideally, a commissioning engineer familiar with panel intricacies should witness the test. A common mistake is sending a project engineer who may lack detailed knowledge of these tests. The testing duration for an advanced release is limited to 1 hour in the factory, while the same release may take 4 to 5 days for testing on site. Therefore, factory experience differs from site experience. Site experience is more robust. Typically, the end user sends engineers to the factory to witness tests and ensure safety. Preferably, a commissioning engineer should witness the FAT test as they know panel intricacies. A common mistake is sending a project engineer as they may miss details. Factories aim to meet needs at low cost, so the right person is essential. It is for the engineer accepting this work to be a commissioning engineer, as they know these panels well. Factories aim to meet your needs at the lowest cost, so the right person is essential. Commissioning testing occurs after receiving panels and is crucial before operation. Release testing has 2 parts, acceptance and final setting testing. During acceptance testing, the release is configured per the drawing and tested on set hypothetical values. To give you what you want at the lowest possible cost, the right man must be in the right place. The commissioning testing phase follows panel receipt and is crucial before operation. Release testing has 2 parts, acceptance testing and final setting testing. In acceptance testing, the release is prepared per the drawing and tested on hypothetical values. Final setting occurs when the final setting document arrives. We retest the release with these specific values. During commissioning, we conduct functional tests for digital inputs, outputs, metering tests for current and voltage inputs, and pickup and timing tests for protective functions. Finally, we check relay logic, ensure LEDs work, and verify the relay model number matches the drawing. The final setting occurs when the document from engineering studies arrives at the station. We retest the relay with final setting values. During commissioning, we conduct functional tests for all digital inputs and outputs. We also perform metering tests for current and voltage inputs and pickup and timing tests for protective functions. In addition to conducting a metering test for all the current and voltage inputs to the relay, we also perform pickup and timing testing for all the protective functions in this relay. Then, we check all the logic inside the relay and ensure that all the LEDs are functioning correctly. Of course, we must not forget to verify that the model number on the relay matches the drawing. We ensure that there are no physical damages on the relay. The commissioning engineer must assume that this relay has not been tested before, as they cannot rely on factory tests as valid tests for the relay. One of the most common mistakes is for the factory engineer to be lenient in testing this panel, claiming that it will be retested again on site. And the site engineer may be lenient in testing this panel, claiming that it has been tested before in the factory. Therefore, it is preferable for the factory engineer to assume that this panel has not been tested on site, and for the site engineer to assume that this panel has not been tested in the factory. This is where the consultant's role comes in, to protect the end user. Otherwise, the end user will be the only one at a loss. Maintenance testing occurs post-station operation. Maintenance tests confirm the relay is still functioning correctly. Previously, electromechanical relays were removed, cleaned, and tested externally to confirm functionality. Now, numerical relays need longer maintenance. Companies debate maintenance frequency: annually, biennially, triennially, or quinquennially. No standard exists. As an engineer, I prefer annual tests. Numeric relays remain in place. They need longer maintenance due to lack of mechanical parts. There is a significant debate among companies regarding updating maintenance intervals, meaning how often should I perform maintenance on the relay? Every year, every 2 years, every 3, or every 5? Honestly, there is no standard regarding this. However, as an engineer, I prefer to conduct maintenance tests on the relay annually. These annual tests include checking the metering to ensure that the relay is still converting the analog signals correctly. It's also important to verify that the internal components remain unchanged, to ensure that no engineer has come during this period to work on the relay without anyone's knowledge or permission. It's also preferable to pull the event record data and analyze it to check if anything unusual occurred during this period. If it's not possible to conduct maintenance tests annually, a schedule can be created that includes all network protections, which is agreed upon internally. Typically, tests are conducted after any malfunction to determine why the relay operated incorrectly or why it failed to operate when it was supposed to. Pulling the event record data and analyzing it to check if anything unusual occurred during this period. we can conduct regular tests to ensure disconnection. If it is not possible to perform maintenance tests annually, a schedule can be created, agreed internally. Typically, tests are conducted after any malfunction to determine why the relay operated incorrectly or why it failed to operate when needed. Thus, we can simulate the same actual fault that occurred by pulling the voltage recorder from the relay in CFG format and placing it into modern testing software to recreate the fault. We can monitor the relay's response to the same fault again and identify the reasons for this malfunction. This process is also known as troubleshooting or post-fault investigation. Therefore, we can simulate the same actual fault that occurred by pulling the voltage recorder from the relay in CFG format and placing it into modern testing software to recreate the fault. This way, we can monitor the relay's response to the same fault again and identify the reasons for this malfunction. This process is also known as troubleshooting or post-fault investigation. The renaissance of a nation